Two objects are dropped from rest at the same height. Object A falls through a distance dA during time t. Object B falls through a distance dB during time 2t. If air resistance is negligible, what is the relationship between dA and dB? I'm going to need a diagram, and I'm going to need an equation. We call this the second kinematic equation, and we said that the initial velocity is 0, so there you have it. Distance fallen is proportional to time squared, and since one of them fell for twice the time as the other, dA is equal to 1/4 dB. Now, a couple people had answered D. I get confused about this all the time. Is dA equal to 1/4 dB or is dA equal to 4 dB? That can be tricky for guys like me, people like me, so I'd say draw a diagram.
The graph above shows the velocity versus time graph for a 3 kilogram object moving in one dimension, and we don't care about mass. Draw a possible graph of position versus time for this object. Well, there's the axis, and we know that the slope on the position versus time graph gives you the value on the velocity versus time graph. Let's take a look at 1, 2, 3, 4 different regions. In the first region, tell me about the velocity. The velocity is negative and the speed is decreasing. So here we have a line segment on the position versus time graph that has a negative slope, but a slope that is getting closer to 0. Again, the slope of the red corresponds to the value of the green. In the next segment, the velocity is positive. It's above 0. The velocity is positive, and the speed is increasing. There's a red line segment with a positive slope that's getting steeper. Oh, and fun fact, the area under the velocity versus time graph corresponds to the total displacement, so we have about equal areas, positive and negative areas, you could say, above and below the time axis. So that means at this time 1 we have a total displacement of 0. Segment 3, the velocity continues to be positive and the speed continues to increase. This red line segment has a positive slope and it's getting steeper. But in the final segment, the velocity, although it's positive, is constant. The line on the position versus time graph has a positive slope but a constant slope. Again, the slope of the red corresponds to the value of the green.
Physics students checking constant acceleration equations. They drop a tennis ball 6 meters. The predicted velocity 20% above the velocity measured by the photo gate. So why is that? We have air resistance. When you first drop the tennis ball, a little bit of air resistance acting opposite the direction of the velocity. As the tennis ball goes faster, air resistance increases. It is related to velocity. A, the ball changes shape while falling. I'll change your shape while falling. B, the acceleration of gravity. No, the acceleration of gravity never varies. Get out of here with B. C, air resistance increases the acceleration of the ball. A lot of people put C. That was the most popular answer. Air resistance increases. Well, you see air resistance and you're like, yeah, it's air resistance. But it's not C. It can't be C. Look at air resistance. That's not increasing your acceleration. Air resistance is fighting against your acceleration. Eventually, air resistance is so great that you are at terminal velocity. Air resistance does not increase it decreases your acceleration. Get out of here, C. What about D? The acceleration of the ball varies with the velocity. Yeah, I think that's it. What about E? The acceleration of gravity change. No, it's not E. It must be D because the acceleration of gravity never changes. A bubble starting at the bottom of a soda bottle experiences a constant acceleration A as it rises to the top. Haven't they ever heard of viscosity? It would travel at a constant speed. Anyway, takes time t. How much farther does it travel in the last second of the journey than in the first second? Yikes! There's the equation. There's the part we care about. There's the path of the bubble. This is how far it goes in the first second. This is how far it goes in the last second. So we have 1, 2, 3, 4 distances to care about. There's the first two. Starts at 0. 1/2 a1 squared. There's the second two distances we worry about. There's a little bit of subtraction. That's how far you go in the first second. There's a little bit of rearranging and then a little bit of subtraction. And then we have to find out how much farther it goes in the last second than the first second. So that gives us this. The equation's not so bad until you use it 8 times.